Okay, today we're going to look at section 5.3, but just I'm going to call this part 1. There are so many vocabulary words and different ideas in this section that I don't want to overwhelm you with all of it in one video. So I'm going to talk through a couple of examples and theorems, and then stop and you work a few problems from those things, and then I'll send out another video for the second part. So we did a little paper folding project in class the other day where we took a triangle and we folded it certain ways, and we talked a little bit about how it was going to illustrate these theorems, Theorem 5.6 and Theorem 5.7. So before we can understand those theorems, we need to understand what a couple of vocabulary words are. So if I have 3 or more lines that intersect in one point, they're called concurrent. So the lines are concurrent. The point where they intersect is called the point of concurrency. So Theorem 5.6 says the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. Now we saw that when we folded we had a triangle that we had cut out. I think we used the right triangle, but any triangle that we were using should work. I was folding the sides so that they matched, so that I could find the perpendicular bisector of each side. And so I did 3 folds, 1 for each side, and so that they were perpendicular. Now my picture's not very good, but they intersected in a point inside the triangle is what we found. So that point where they intersect, the point of concurrency, should be the same distance from each of the vertices. So if I were to measure from that point to the vertex, each of them should be the same. Now my drawing's not very good and doesn't illustrate it very well. I have a better drawing on the next page that we'll look at in a minute. All right, that was the first way that we folded the triangle. The second way that we folded the triangle was to try to split the vertices in half. So we were doing the bisectors of the angles. And when we did that, we came up with a point. We also had a point of concurrency, but that time that point was equidistant from the side. So we're going to look at a couple of examples, one of each from each theorem, and see kind of what this looks like and what it means. Okay, so for the first one, my drawing's not perfect. The one in the book is much better, but I did my best to try to get it on here. This is going to illustrate 5.6, Theorem 5.6. So in this triangle QRS, I have the perpendicular bisectors of the sides in purple. And what I've done, I drew all of those in, and then I found the point where they intersected. Okay, that point was here where there's a C marked. It's kind of hard to see. I'm going to make it red. It's here where they all 3 intersect, so that point of concurrency. Now Theorem 5.6 says that point of concurrency is equidistant from the vertices. So if I measured from C to S, that should be, wait a minute, yes. So S to C, I'm putting it in the wrong order. S to C, Q to C, and R to C. So from that point of concurrency to each vertex, those distances should be the same. And so that's what's written right here. QC equals SC equals RC. All right, so QR and S are equidistant from C, but what I have here, this red point at C, is called a circumcenter. And what that means is if I were to use that as a center of a circle that I could draw around the triangle QRS so that it only touched the vertices, then that would be the center of the circle. This circle that's drawn around it is said to be circumscribed about the triangle. So think about what circum means. Circumference is a word that we use when we talk about the distance around a circle. So we've drawn a circle. Described means to write or draw. So this circle is drawn around the triangle, and it's only touching at the vertices. So that is a circumscribed circle, and its center is the circumcenter. All these vocabulary words, you need to start getting on Quizlet now and studying, because when we have a quiz, it's going to be hard to keep them straight if you don't. Okay, so example 1 is using Theorem 5-6, and it asks us to find the center of the circle that you can circumscribe about triangle OPS. So I went ahead and copied the picture of the triangle that was drawn. So we've got it on a coordinate axis, and O is drawn at the origin. We're at 0, 0. And then I drew in P and S like they did. So this one, the P is 1, 2, 3, 4, 5, 6 up on the y-axis, and S is 4 over on the x-axis. So what they're asking me to do is find the center of the circle. So now let's think about what we just saw in the picture before this. Let's go back for a second. The circumcenter was the one that I could find by finding the point of concurrency of the perpendicular bisectors. So if I want to find that center of the circle that could be drawn around the triangle, then I need to draw the perpendicular bisectors and see where they intersect. And that point of concurrency will be my circumcenter. So what I'll do is I'm going to start by drawing in the perpendicular bisectors of the vertical and horizontal sides, so from O to P and from O to S, because those are the easiest place to, first of all, find where it's bisected and make it perpendicular. So if I'm looking at OP, and I know P is at 6, so I would go 1, 2, 3 up, and that would be bisecting the side, so cutting it in half. And then I want to draw a line that's a perpendicular line to OP. Well, so if it's a vertical line, then a horizontal line would be the what's perpendicular to it. So I would just draw that line. This is a perpendicular bisector of OP. Okay, that's one of them. Now remember, the circumcenter, or the center of the circle that I can circumscribe about the triangle, will be where the perpendicular bisectors intersect at that point of concurrency. So now if I draw another one from O to S, so here halfway the length of the line would be at 2, and then I would draw it, since OS is a horizontal line, I would be drawing it vertically to make it perpendicular. Okay, so here I found where these two lines intersect. Now I could draw in the third perpendicular bisector, but since they're all going to intersect at the same point, I don't really have to draw another one in. The perpendicular bisector of PS should also intersect here at this point. Okay, so, and actually I think if I had this drawn right, I believe when I drew it on my paper, it really ends up being that it is intersecting the side PS, right on that side. But my picture's not very good. Okay, so from here then, that would be the center of the circle that I could draw around it. Now I certainly won't be able to do this right, but you should theoretically, if you had your compass, be able to put your compass at the center where that point of concurrency is and measure to one of the vertices, and that would be the radius of your circle, and you could just draw the circle around it, and it would only touch the vertices and not any other part of the triangle. Okay, so when they ask you to do these type of examples, you need to make sure you understand what they're asking for. So they're asking me to find the center of the circle that you can circumscribe about a triangle. That's the circumcenter. That uses Theorem 5-6 and the perpendicular bisectors of the sides. Okay, so I want y'all to try quick check one. Pause it. On this one, well, wait, don't pause it yet. Find the center of the circle you can circumscribe about the triangle with vertices 0, 0, -8, 0, and 0, 6. So draw those first to make your triangle, and then see if you can figure out where the circumcenter would be. Okay, so I'm going to put these points in. Here is 0, 0. -8, 0 would be 1, 2, 3, 4, 5, 6, 7, 8 here. And then 0, 6 would be on the y-axis, 1, 2, 3, 4, 5, 6, because the x value is 0. My dots are a little too big. So here's my triangle. There are two sides that one is horizontal and one is vertical. So I would actually proceed just like I did on the example here. I would find the bisector of the vertical and horizontal sides. So 1, 2, 3. It's going to be at 3 because that was 0, 6. And I'm going to draw it a horizontal line so it'll be perpendicular. And then here, this was negative 8, 0. So it's going to be at negative 4. That's halfway. And I'll draw a vertical line since it's bisecting the horizontal line. Okay, so here is where those two intersect. That would be the center of the circle that's circumscribed about it. So if they're asking for a point, then that would be the point 1, 2, 3, 4, negative 4. And the y value would be 1, 2, 3. I guess we didn't say what it was on the example before this. On the example before this, it would have been at the point 1, 2 on the x-axis and 1, 2, 3 on the y-axis. Now notice that the x value is exactly where that midpoint went on the line OS. That x value, and the y value is the y value of the point that went on the line OP. So it's where those two intersect. They each had a 0 in one place or another, and so these were the parts that weren't 0. Okay, let's see what it looks like for Theorem 5.7. So this time, this picture is actually almost harder to draw than the other one. We've got, this time, Theorem 5.7 talks about having angle bisectors drawn and that they intersect in a point of concurrency. So at T, I've got the angle bisector drawn in. You can see that my angles are marked with one hash mark to show that they're equal. I have an angle bisector drawn at U and at V, and so they intersect in the point I, here in the middle. That point, according to Theorem 5.7, is supposed to be the same distance from each of the sides. So if I drew, remember when we measure from a point to a line, we have to measure with the perpendicular distance. So I've drawn in from I to the side UT, and I've called it X there, a perpendicular measurement. And then I went from I to Y using a perpendicular line, and from I to Z. Now, according to Theorem 5.7, the distance from I to X, I to Y, and I to Z should be the same. So that's what this is telling me. Xi equals Yi equals Zi. So those links are the same. Just written differently, the points X, Y, and Z are equidistant from I, the end center. So the one we looked at where the circle was circumscribed about the triangle, we called that a circumcenter. Now we're calling I an end center, and this circle is not drawn around on the outside of the triangle, but rather it's drawn on the inside. So it's called inscribed. It's drawn on the inside of the triangles. It touches the side of the triangle in one point. My drawing doesn't show that very well, but that's what it should be. Okay, so here on example 2, they tell us that a family, the Jacksons, they want to install the largest possible circular pool in their triangular backyard, and they want to know where that would be located. So what I did was I just drew a picture of a triangle and said this is a triangle-shaped yard. How could I put a pool inside that yard that would be as large as possible? Okay, so if we think about Theorem 5.7, if I can find the center of the circle that would be inscribed in here, very hard to draw. The largest one would be the one that was the same distance from each of the sides. Otherwise, it would be closer to one side of the yard or another, and it would be a little bit smaller. So the largest way we can do it is to have those distances be the same to each of the sides. And so the question is, how would I figure out where that is? Okay, so according to theorem 5.7, if I were to draw in the angle bisectors of each of the vertices, then I should get, so those two angles will be the same. If I do it again on this one, it's hard to draw, my line moves over. And I also bisected that angle at the vertex. That where they intersect should be the center of the triangle that's inscribed, which is the largest one. If I didn't have one that was inscribed in it, I just had a circle within it, the inscribed means it's touching each of the sides. So if I could have a pool right here, where this edge is not touching the side of the triangle. But clearly that looks smaller than this one would be, even if the triangle was the same. So the largest one that I can have is one that actually touches the sides in one point. And that would be the one that's inscribed, like the one we've drawn here. Okay, so I'm going to stop there. I'm going to send out an assignment that tells you which problems to work through after you watch this video. And then I'll send out another video later.